Hello everyone, welcome to my channel. This is Karuna teaching the course Computer Architecture and Organization. Fifth unit contains the following topics, out of which in this video we are concentrating on some more basic memory circuits and memory system consideration. Let us see synchronous DRAMs. This topic comes under basic memory circuits. Let us see. Already we know the structure of the memory. In previous video we have discussed about this. Okay, so this is the memory, contains cells. Those cells are arranged in the form of rows and columns. Row address latch, and this is column address counter. This is row decoder. This is column decoder. Here read or write circuits and latches means sense or write circuits. Next, column address counter will be refreshed or reset with the help of refresh counter, and whatever the address is transferred to the memory by the processor, that will be loaded into row address latch and column address counter. Now row decoder selects one of the memory location out of all memory locations according to the address bits present in row address latch. Okay, so these two, row address latch, column address latch, are controlled with the help of mode register or and timing control. Here RAS, row address strobe, and column address strobe. These two signals are used to activate the row address latch and column address latch. Okay, whether read or write operation is performed based on the read or write signal issued by the processor. So RAS, CAS, CS bar, these are all active low signals. Why we call it as synchronous DRAMs? Because operation of this DRAM is directly synchronized with the processor clock signal. Okay, so here data input register, data out registers, which are used to store the data bits. Okay, so data bus is a bidirectional bus. That's what this bus indicates. Two arrows. This is for data out and data in. Synchronous DRAM. That means the operation of this DRAM is synchronized with the processor clock. Okay. So the outputs of sensor circuits are connected to the latches during read operation. Okay. Then processor issues read signal, active high signal to the mode registered and time control circuit. During read operation, the contents of cells in a row are loaded onto the latches. Okay, so during refresh operation, the contents of the cells are refreshed without changing the contents of the latch. Data held in the latches correspond to the selected columns or transferred to the output. For a burst mode of operation means successive columns are selected using column address counter and clock. Okay, so CAS signal is needed to generate externally. A new data is placed during rising edge of the clock. Now let us see the burst mode of operation. This figure shows timing diagram for a typical burst read of length 4. Here burst contain 4 data bits D0, D1, D2, D3. That's what we can say. This burst length is 4. Now this is clock cycle. All operations must be synchronized with the clock cycle. Okay, so you know these are all control signals: read or write bar, row address strobe, column address strobe, address bus, data bus. Group of lines we can say control bus. Let us see the operation. First, the row address is latched under the control of row address strobe. Here row address strobe is active low signal. Okay, during which row address is placed on the address bus. Now after some clock cycles, or we can say the memory typically takes 2 by 3 cycles to activate the selected row. Then column address is latched. See, this is column address strobe, active low signal. Okay, so column address is latched under the control of CAS. Whenever CAS is active low, then column address is placed on the address bus. After a delay of 1 clock cycle, see this is 1 clock cycle. Okay, after delay of 1 clock cycle, the first set of data bits is placed on the data lines. So after placing this, the SDRAM automatically increments the column address to access the next 3 sets D1, D2, D3, because our burst length is 4. The 3 sets of bits in the selected row are placed on the data lines in the next 3 clock cycles. This is first clock cycle, next. Okay, 3 clock cycles. During these 3 clock cycles, the remaining data sets are placed on the data line. Okay, likewise data will be transferred with the help of this data bus. Under the control of all these control signals must be synchronized with the clock cycle. That's what we can say. This DRAM is nothing but synchronous DRAM. So this DRAM built-in refresh circuitry contains refresh counter, which provides the address of the rows that are selected for refreshing. Let us see some important points we have to remember: memory latency, bandwidth, and double data rate, synchronous DRAM. Okay, so let us see what is meant by memory latency. It is the time it takes to transfer a word of data to or from memory. Coming to the memory bandwidth, it is the number of bits or bytes that can be transferred in 1 second. Coming to the difference between synchronous DRAM and double data rate synchronous DRAM. Synchronous DRAM performs all actions on the raising edge of the clock cycle. Okay, I told you raising edge from low to high. Double data rate SDRAMs. This memory transfers the data on both edges of the clock, and their bandwidth is doubled for long burst transfers. Such devices are known as double data rate SDRAM. Next, let us see the structure of larger memories. Let us see the organization of 2 mega into 32 memory module using 512K into 8 static memory chips. Okay, for example, we need to construct 2M into 32. 2M means 2M memory locations. 32 means 32-bit data. To address 1M, we need 20 address lines. To address 2M memory locations, 21 address lines are required. Assume only 512K into 8 static memory chips are available in market, but we have to construct 2M into 32. Okay, so we can construct this memory with the help of these chips. Let us see how it will be. Okay, so the available chips are 512K into 8. With these chips, we have to construct 2M into 32. 2M into 32 equal to 64 mega cells are required to construct memory. With the help of 512K into 8, to construct this 64M, we need 16 512K into 8 memory chips. 8 means byte. So we can write it as 512 KB. Okay. 16 into 512 KB. So 16 512 KB chips are required to construct 2M into 32. Let us see how 2M into 32 memory module can be organized with the help of 16 512 KB. Okay, let us see the structure of 512K into 8. To address 512K memory locations, we need 19 address lines. That's what here mentioned, 19 bit address bus. Okay, this is 512K into 8 memory chip. Okay, so we require 16 memory chips to construct 2M into 32. Each memory location stores 8-bit data. Okay, that's what data bus length is, 8 bits. Okay, each memory location stores 8 bit, but we need to store 32 bits. Okay, so but chip can store 8 bits. Okay, let us see how it will be reorganized. So 16 512 KBs are arranged like this: 4 rows and 4 columns. Okay, 4 by 4 equal to 16. So 16 memory chips can be organized like this, each memory having 512K memory locations, and each memory location stores 8 bits. Here we need to store 32 bits. That's what first chip can store 8 bits, and next 8 bits, 8 bits, 8 bits. Okay, so 4 8s are 32 bits. If you organize memory chips like this row of memory locations can store 32 bits. Okay, that 32 bits can be accessed at a time by selecting all these 4 chips which are connected to that row. Okay, so let us see how these chips are to be selected. Okay, so 512K into 8 memory chip requires 92 bit address. Here 2 power 19 equal to 512K. 19 are the address bits are used to point the 512K locations. We have 21 address lines. Let us see how these 21 address lines can be used in case of 512 KB memory chip. Okay, so first lower order bits A0 to A19 can be used to address 512K locations of 512K byte memory chip. Okay, next higher address bits 19 and 20 used as two input lines of 2-bit decoder. So this decoder inputs are 2 bits and outputs are 4 bits. We'll get 4 combinations. 2 bits are used to select rows. 21 address lines are divided into 2 address lines and 19 address lines. 19 address bits are used to access specified byte locations inside each chip of the selected row. 2 address bits are used to select chips in a row with the help of chip select signal. Only the selected chip places data on the data output lines. Okay, see, first chip consists data bits D0 to D7. Next chip having D8 to D15 data bits. Next chip consists D16 to D23. And last chip consists D24 to 31 bits. Total 32 bits can store. Okay, then total 32 bits can be accessed at a time by selecting the row of memory chips with the help of A19 and A20 address lines through 2-bit decoder. Likewise, we can access any data from any row of memory locations. A0 to A19 bits are used to access specified byte locations inside each chip of the selected row. Each chip has a chip select signal. With this, you can select the required chip. With the help of read-write control signal, processor can read the data from the memory or write the data to the memory through the data lines. Likewise, 2M into 32 memory module can be constructed with the help of 512K into 8 static memory chips. Coming to the memory system consideration. To reduce the number of pins, multiplexed address lines can be used. In order to achieve the multiplexing, memory controller circuit is needed to insert between the processor and memory. Let us see how the operation, whether it is read or write, is to be controlled with the help of memory controller. Okay, so here memory controller is placed between the processor and memory. So the signals present between processor and memory controller are address lines, read-write control signal, request line, clock cycle. Okay, this is synchronous RAM. That's what we are using, clock signal. Okay, next memory controller and memory. Okay, so the signals existed between memory controller and memory row or column address bus, row address stop signal, column address stop signal, read or write signal, chip select signal, clock signal. Okay, to see the working of this memory controller, initially processor issues all bits of an address. At the same time, the required multiplexing of address bits is usually performed by a controller circuit between processor and memory. The controller accepts a complete address and read-write signal from the processor under control of request signal, which indicates that a memory access operation is needed. Then the memory controller forwards the row and column portions of the address to the memory and generates row address stop and column address stop signals. Thus, the controller provides the row address stop and column address stop timing in addition to its address multiplexing function, and also sends read-write signal, chip selection signals to the memory. Here all these are active low signals. Okay, so this is synchronous DRAM. That's what it requires clock signal. Upon the control of all the signals, data will be transferred between the memory and processor with the help of memory controller. Thank you. We will meet in next video.